Hello everyone, I'm Masanori Hirano from the University of Tokyo. So in this presentation, I talk about data-driven agent design for additional market simulation. At first, I'll talk about our motivation. Recently, there is a significant instability in financial market. For example, 2008 financial crisis, or flash crashes, or recent very big price fluctuation caused by COVID-19. So, to dealing with those problems, regulations are necessary. For example, new regulation called Basel III is established in the last decade. However, there is a big problem. Can we avoid those big crises again? So this is very difficult question because in financial market there is a non-stationarity in financial market and also rare phenomena happens frequently. So handling those problems, simulation is a good solution. However, I think there is a trustability problem. Artificial market simulation is one example of simulations for financial market. This is a kind of model-driven approach, and so simulations are run on the computer using virtual market, so we can test hypothetical situations. This is very promising approach for financial market analysis. However, there are some problems. Usually, models are human-made, so human can overpass key features which have to be built in the simulation model. So I doubt that these simulations are realistic or not. So I think the model based on data is necessary for this framework. In this work, we are comparing the traditional simulation model versus our new simulation model using our data. So in this study, we only focused on HFTMM, which is a very specific trade and strategy in the market. And in our target is Tokyo Stock Exchanges, and we analyze the special data provided by Japan Exchange Group. This is the explanation of the data we used in this study. The data we used in this study is called order book reproduction data that is provided by Japan Exchange Groups, and this data specially containing masked trader information called virtual server, and using this information we can almost identify which orders come from which traders. As I said earlier, we only focus on the HFTMM, and then the HFTMM is the abbreviation of high frequency trade market making strategy. So this is the combination of the market making strategy and high frequency trading. So at first, market making strategy is the strategy making the many orders near the best prices. In this example of order book, they make many buy orders at 999 yens, and then the many orders on the sell orders on the 1001 yens, and getting profit between those prices called the spread, and do repeatedly they get plenty of monies. However, this strategy have significant risks because the price movement usually outnumbers the spread, because so to hedge the risk they do their action very faster and hedging risk by setting off their inventory very faster before the big price movement. So the reason we focus on this strategy is three reasons. One is it is very easy to identify this data in the big data because of their unique behavior. The second reason is the simulation for HFTMM model is exist and well known. And then the third reason is we cannot handle all the data because of computational limitation. Just we limit the data to the HFTMM. Here is the extraction procedures for HFTMM. At first step of extraction, we filter only the HFT traders based on the one indices action particle. And in the next step, we calculate some indices, and in using those indices corresponding to HFTMM, we perform the hierarchical clustering, and we successfully extracted HFTMM traders. This procedure is based on the previous research. Next, I'll talk about the simulation model. In our simulation model, there are two types of agent and one market. Two types of traders are standard traders and HFTM traders. And standard trader agent is based on the previous work, and this trader makes their orders based on three factors: fundamental and chart and noise. And another trader called HFTM traditional agent is also based on the previous work. And in this model, their trader make their orders as a result of optimization solution for HFTMM, and this algorithm is also used in the actual financial market. So using those traders, the artificial market simulation runs. And in this simulation, we also employ the order delay and information delay for style trader, because usually HFTMM trader publish their orders very fast and get their information also very fast. Because realize this feature, we employ the order delay and information delay. So using this simulation, as a next step, we compare the HFTMM traders' behavior in the simulation and in actual data. So here is a comparison result of ordering behavior of HFTMM. And in this figure, actual data and simulation data are compared. Blue bar means actual behavior of HFTMM, and orange bar means HFTMM traders' behavior in simulations. And the horizontal axis means ticks from the best prices. According to this result, there is a significant difference between the actual behavior and the simulation behavior. So we think we have to deal with difference. Just dealing with the difference between simulation and actual data of HFTMM traders' behavior, we made the deep learning-based model to replace the traditional HFTMM agent. So in this model, we built the model based on the deep learning architecture using the actual data. So we made the 9 patterns of architecture of deep learning, and to build the model, we employ the next order prediction. In this prediction, using the market state and traders ordering state, they make the next order prediction in each traders. So through these prediction tasks, GL-based model can predict the future actions of each traders, and using the model, we can run the simulation. So here is the experiment outline. So in our experiment, we change HFT model among the traditional one and some 9 patterns of deep learning-based HFTMM models. So as a first step of our experiment, we test the learning capability of deep learning-based model. In this experiment, we analyze how well deep learning-based model can predict the actual next orders. Then, the second step of our experiment, we make a simulation test. In this test, we compare each model's performance in simulations and compare the HFTMM traders' behavior in simulations and the actual HFTMM traders in actual market. So compare them, we can get which model is more natural in the natural make the natural orders and also in the simulation environment. As a criteria of the comparison, we employ the MSE and KLD of order position probability from the best prices, which means that the lower score means a better performance. Here is our experimental result. In this figure, there are some dots with each dot represents each deep learning based model, and then the horizontal axis means MSE in running, which means that the running capability of each deep learning based model. On the other hand, the vertical axis means MSE in simulations, which means that how natural behavior each deep learning based model shown in the simulation environment. And then the red uh, line means that performance of the traditional HFTMM models in simulation environment. According to this result, there are two outperforming models than the traditional HFTMM models, which means that our deep learning based approach can work in the two models. However, there is a reverse relationship between the MSE running and MSE simulation, which means that the better trained model in actual data means worse behavior in simulations. This is very, very interesting. So we analyze more about this. According to our additional analysis, we found that the number of parameters in deep learning model are key of the reverse relationship between the running performance and the simulation performance. It means that there are more parameters in deep learning model. The model can be trained better. On the other hand, there are more parameters in deep learning model. Simulation performance are getting worse. We assume the reason is some of data generated by simulation seems partially out of data of actual market. We think there are two possible reasons. One is simulation is not refined enough. The other reason is data we used in this study is very specific because we used data only in Tokyo Stock Exchanges. On the other hand, the simulation employed in our study is a very generalized one, thus it could be a possible reason. Here's our conclusion and our future work. So in this study, we propose a trader model based on deep learning and actual data. So some of our proposed models show better performance in simulation environment, and this suggests that deep learning-based agent using actual data is one promising solution. We also found that the number of parameters in deep learning model is important to avoid degrading performance in simulations. It is very, very interesting. So as a future work, we should address on the other agents than HFTMM in terms of deep learning based traders agent, and we also search for the best parameter size and architectures for the simulation. And then the auto ML tuning for this task is also future work. Thank you for listening.